This section is on inverse relations and inverse functions. Okay, so let's start out with a simple relationship, y equals x squared, and let's make a table of values for this. All right, so if x equals 0, y equals 0. If x equals -1, -1 squared is 1. 1 squared is also 1. If x is -2, y is 4. And if x is 2, y is also 4. And then when we graph this, we get this nice simple little parabola, as we would expect. Okay, but now what we're going to do is we're going to reverse these coordinates. We're just going to flip the x's on the y's. And when we do, we will get the inverse relation. All right, so we're just going to flip each one of these. 0, 0, obviously it's just 0, 0. But this becomes 1, -1, 1, 1, 4, -2, and 4, 2. And when you plot this, all right, what you will get is this, a sideways parabola. And this is the inverse of f, okay, expressed as f to the -1 of x, okay. Now, notice the domain and the range. The domain of the original function is all real numbers, while the range is positive values of y, including 0. Now, for the inverse, the domain is positive values of x, including 0, while the range is all real numbers. Notice that the domains and the ranges are flipped, okay, are switched. So this will be true for relations and their inverses. The domain of f of x is the range of its inverse, and the range of f of x is the domain of its inverse. Okay, so if you know one, you know the other. Just flip-flop them. All right. Now, by the vertical line test, f of x is a function. Okay. While by that same test, the inverse is not. Okay. Well, how do you know if a function has an inverse that is also a function? Okay. Well, there is something called the horizontal line test that will help us. All right. And it is stated as such. The inverse of a relation is a function. The inverse of a relation is a function if and only if each horizontal line intersects the graph of the original function in at most one point. Okay? So that's kind of a mouthful here. The inverse of a relation is a function if and only if each horizontal line intersects the graph of the original function in at most one point. Okay, now this actually fails the horizontal line test. So that tells us that its inverse is not a function. Okay. All right. A word about this if and only if notation. If and only if is something in mathematics that indicates that a statement goes in both ways. If the inverse of a relation is a function, then each horizontal line intersects the graph of the original relation at most one point. That will be true. But the reverse will also be true. If each horizontal line intersects the graph of the original relation at most point, then the inverse of a relation is a function. All right, so if and only if is a statement that you'll see in mathematics, and it states a slightly more rigid condition. Okay, the if-then goes both ways. If this, then this, and if this, then this. Okay, so you'll see this from time to time. Anyway, this horizontal line test can be used with any relationship. The vertical line test will tell if it's a function. The horizontal line test will tell if its inverse is also a function. Let's do an example. So let's take this graph right here. Okay, part A, is this relation a function? Well, by the vertical line test, the answer to that would be yes, because each vertical line only intersects the graph once. All right, what about part B? Does this relation have an inverse that is a function? That is, does it pass the horizontal line test? And the answer to that is yes. So this is a function, and its inverse is also a function. What about this one? Is this relation a function? Yes, because it passes the vertical line test. Okay. Is the inverse of this a function? And the answer to that would be no, because a horizontal line would intersect this graph more than once. In fact, it would intersect it 3 times. So while this is a function, its inverse is not. What about this? this ellipse. Okay, well, this is not even a function because it doesn't pass the vertical line test. It also doesn't pass the horizontal line test. So neither this relation nor its inverse is a function. All right, finally, what about this one? Is this a function? And the answer is yes, because it passes the vertical line test. X equals -2 and x equals 2 are actually asymptotes. Does it pass the horizontal line test? And the answer is no. So its relation, so this, while this relation is a function, its inverse is not. If a relation passes both the vertical line test and the horizontal line test, then they are both functions and are one-to-one. All right, and one-to-one means that every x is paired with a unique y, and every y is paired with a unique x. Okay, now what do we mean by that? Well, let's go back a few units and where we looked at this set of data points, and we discussed whether this was a function or not. And you might see a couple of red flags right there. There's a -1 is mapped to a 2, and a -2 is mapped to a 2. But that's a function, remember. If the inputs do not repeat, then it's a function. Okay? The outputs can repeat, but the inputs cannot, and then it's a function. Now, to get the inverse, let's just flip-flop the ordered pairs, and notice now the inputs repeat. So the inverse is not a function. Okay? If they did not, if for example this were a 6 or something like that, then this would also be a 6, and then the inputs would not repeat. So if the inputs don't repeat and the outputs don't repeat, if neither of them repeat, then it's unique, they are unique, and it's a one-to-one function. Okay? If the inputs don't repeat, then it's definitely a function. If the outputs also don't repeat, then it's one-to-one. Okay, so that's the test. All right, next, we want to find an inverse function algebraically. Now to do that, we exchange x and y in the equation and then solve for y. For example, let's take the f of x being x over quantity x plus 2, and let's find an equation for the inverse. Okay, well, the first thing I'm going to do is instead of f of x, we're going to write y. Okay, so I'm just substituting y in for f of x here. Then we're going to exchange the x and the y. So just where there's a y, write an x, where there's an x, write a y, like that. Okay, well, that's the easy part. Now what we need to do is to solve this for y. I want to get y equals something. Okay, and that's a bit of a chore. Okay, what we have to do first, unless you like algebra like I do, so one of the things we do first is to get rid of the denominator. I'm going to multiply both sides by y plus 2. That's going to cancel out the denominator here, and what we're going to be left with, turning it around, is x times the quantity y plus 2 is equal to y. Okay, now I got to get all the y's together. All right, so to do that, I'm going to first distribute the x, y, 2x. Then I'm going to get all the y's on one side by subtracting xy from the left-hand side. We get this, okay? Moving that up here. Now I'm going to factor out this y, all right? Factor out the y. And then finally, divide by 1 minus x. And after canceling the stuff on the right side, we finally get an equation for y. So y equals 2x over quantity 1 minus x, and that is the inverse. Okay, so what do we do here? We first just wrote in a y there, all right, and then exchange the x's and the y's to get x equals y over y plus 2, which we then have to solve for y. So you take various algebraic operations to isolate the y, and in this case we get this. Okay, so that's how to algebraically determine the equation for the inverse of a function. All right. Now, we want to graph this in Desmos, okay, just to see what it looks like. And it ends up looking like this, okay? The original function, all right, is the one in reddish, okay? And its inverse is in blue, okay? Now notice that inverse functions reflect across the line x equals y. If you write in the line x equals y here, okay, that x equals y is an axis of symmetry, and it acts as a mirror from one side to the other. So if I take points on, say right here, if I take points on this side of x equals y, go an equal distance on the other side of x equals y, then I get its inverse. So I can take points on the original function, cross perpendicularly the axis of symmetry an equal distance, and we will get points on the other side. Saying that another way, if you had ordered pairs, an ordered pair here, if you flip-flop the coordinates, you would get an ordered pair there. Notice this is like 0.85, okay, and about 5, 0.8. The ordered pairs are flipped, okay? So in functions and their inverses, or relations and their inverses, I should say, reflect across x equals y. That's an axis of symmetry. Next thing we want to do, let's say f of x is this, all right, and we're going to assume they're one-to-one, and we're going to find the inverse by making a table of values, okay, and then exchanging x and y, and then we'll do these things in order. So let's do part A first. Let's make a table of values. And so if x equals 0, 2 times 0 is 0, plus 1 is 1. All right, if x is 1, 2 times 1 is 2, plus 1 is 3. If x is 2, 2 times 2 is 4, plus 1 is 5, and etc., etc. And we get this for our table of values. And then to get the inverse, just reverse the coordinates. All right. So reversing the coordinates, reverse the coordinates, reverse the coordinates, and we get those. All right. So this would be the inverse. Okay. Now let's find the inverse by exchanging x and y in the original equation and solving for y. So first thing we do is substitute y in for f of x, and now we want to solve this for y, which is a little bit easier than our last examples. We just have to, oh, sorry, I missed a step. We have to exchange the x's and the y's. Yes, exchange the x and the y's. Now solve this for y by subtracting 1 and then dividing out the 2, okay? And you get this. You could leave this as x minus 1 over 2. I prefer to write it like this. And then I want to indicate that that is indeed the inverse rather than the original function. So we're going to write it as this 1/2 x minus 1. Okay? So that's the equation for the inverse. Part C, in Desmos, show that the inverse found in part A with the table of values and the inverse found in B, the equation, let's show that they are the same. Okay, so I plotted, this is the original function, 2x plus 1. And here is the one from part A, and we just get a set of data points, right, like that. And then I plotted the line that we found in part B. Now, how do the data points in part A match up with the line in part B? Well, they're the same, okay? So here I plotted them all in the same window, all right? And the data points in A match up with the line, the equation of the line that we found in B. So that does indeed show that they are the same, all right? And then finally, part D, does the red and the blue reflect across x equals y? Well, if I sketch in x equals y, notice that it is indeed a mirror, okay? A mirror. These points are equal on opposite sides. So whereas this has a data point 5, 2, this has a data point 2, 5, okay? And correspondingly with the other points. So it does indeed reflect. Okay, one more thing to do in this section, and that's to verify inverse functions. And inverse functions undo each other. What that means is f of g of x is equal to x, and g of f of x is equal to x. They more or less cancel each other out. So you end up, if you input an x and you put it through the composite functions, okay, you end up with the same output, x. It doesn't change it, okay? All right. So, for example, let's show that this function, f of x equals x squared, and g of x is square root of x. Let's show that these are inverse functions, okay? And to do that, what we're going to do is find f of g of x. And f of g of x is going to be f of the square root of x. Well, what do? Anything inside the parentheses, we just square it, right? Well, the square root of x squared, all right, is just x. Okay, we knew that from like math 1 or whatever. So f of g of x is indeed equal to x. Okay, so we tested that condition. We also have to test the other condition. Okay, so g of f of x is equal to x. Well, we got to test that. Well, let's see. That's going to be g, if f of x is x squared, g, we take everything and just put it underneath the radical sign. So we get the square root of x squared, which we also know is equal to x. So that also checks out. Okay, so inverse functions undo each other. So if to test for an inverse, take f of g of x, input the x into this function machine as we could say, and if it outputs the same as you input, then it's an inverse. You have to test both conditions. You have to also test g of f of x, and that if that also comes out to x, then you know that they are inverse functions. Okay, so those are some properties about inverse relations, relations and their inverses. Okay, so time to do some practice problems.